Tokyo, 10 March 1945, 0100 hours. At first light, aerial reconnaissance mosaics showed approximately 16 square miles of central Tokyo missing from the map. 21st Bomber Command computed approximately 88,000 dead in a single night, the highest fatality count of any air raid of the war. The weapons were not atomic. They were 6-pound M69 incendiary bomblets released from B-29 superfortresses in E-series clusters, engineered to ignite wood and paper construction. The official mission summary logged 1,665 tons of incendiaries dropped by 279 aircraft in under 3 hours. Before March 1945, high-altitude precision attacks produced poor results over Japan's jet-stream-scarred skies. In one operation, that doctrine inverted night, low-altitude incendiary saturation. The outcome was not random, it was planned, resourced, and executed through a chain of technical and logistical decisions that converged at Tokyo. Mariana Islands, Guam, Saipan, Tinian, November 1944 through February 1945. Mission reports stacked on 21st Bomber Command's operations table. Altimeter photographs and bomb plots marked in red circles covered the plywood surfaces. Intelligence officers leaned over the images, grease pencils in hand, measuring the distance between aim points and actual impacts. The United States Army Air Forces entered the Marianas expecting Norden-guided precision at 25,000 to 30,000 feet against aircraft plants, steelworks, and refineries. Reality delivered something else entirely. Jet streams up to 200 miles per hour scattered formations across the sky. Bomb release gear froze at altitude. Average accuracy fell to approximately 6% within 1,000 feet of the aim point. Bombardiers watched their carefully calculated drops vanish into clouds and wind shear. Major General Curtis E. Lumey assumed command of 21st Bomber Command in January 1945. He inherited 3 bomb wings, the 73rd, 313th, and 314th. He also inherited a failing strategy. Lumey walked the flight lines at North Field on Tinian, watching crews return from missions over Japan. The bomb bay cameras told a consistent story: scattered hits, minimal damage, high fuel consumption, and mounting losses to weather and mechanical failure. The B-29 Superfortress was the most advanced bomber in the world. For Wright R-3350 engines, pressurized crew compartments, remote-controlled gun turrets, a Norden bombsight capable of placing a bomb in a pickle barrel from 20,000 feet, in theory. In practice, the aircraft burned through fuel at approximately 25% above planned consumption at high altitude. Icing plagued the engine cowlings and wing surfaces. Mechanical intervalometers and bomb bay actuators malfunctioned in sub-zero temperatures. The jet stream, a river of air moving at hurricane speeds, degraded Norden solutions and increased circular error probable dramatically. Staff planning documents from January and February 1945 recorded the assessment bluntly. The results of our high-altitude bombing are grossly unsatisfactory. This conclusion appeared in post-mission analyses and staff memoranda at 21st Bomber Command. The numbers supported it. Sortie after sortie returned with reconnaissance photographs showing intact targets. Production facilities remained operational. The strategic bombing campaign against Japan was failing. Intelligence officers examined aerial photographs of Tokyo with increasing frustration. The city did not resemble the industrial complexes of Germany. There were no massive Krupp factories or concentrated refineries. Instead, Tokyo operated as a decentralized manufacturing network. Intelligence briefs estimated approximately 27,000 small workshops scattered throughout the capital, producing subassemblies, fixtures, gauges, and tools. These workshops occupied residential buildings. They operated inside homes and small structures made of wood and paper. Precision doctrine aimed at large plants missed the decentralized reality entirely. Weather and dispersion negated the theoretical advantage of the Norden bombsight. Staff planning sheets began exploring an uncomfortable conclusion. Neutralizing approximately 27,000 workshops could cut approximately 60% of Japan's war output, if the neighborhoods themselves could be burned. The shift in thinking was documented, methodical, and ruthless. LeMay reviewed firebombing studies from European operations. Hamburg in July 1943 had demonstrated that incendiary density above a certain threshold could trigger self-sustaining urban combustion. The phenomenon was called a firestorm. It required specific conditions: fuel load, wind speed, ignition density, and urban geography. Tokyo possessed all of them. Guam, 19 February through 28 February 1945. LeMay signed a night operations directive in his headquarters building. On a side table lay comparative plots from Hamburg 1943, showing firestorm thresholds calculated by British analysts. The European model suggested that incendiary density equal to or greater than approximately 25 tons per square mile could trigger self-sustaining urban combustion under favorable wind conditions. United States planners expected improved per sortie effectiveness by trading defensive guns for payload and altitude for accuracy. The theory was simple. Lighter aircraft could carry more bombs and fly more efficiently at lower altitudes. Lower altitudes meant better accuracy and less interference from jet stream winds. Night operations would reduce the effectiveness of Japanese fighters and anti-aircraft guns. The weapon was already proven. The M69 incendiary bomblet weighed approximately 6 pounds. It contained gasoline gel and a magnesium ignition core. A timed fuse allowed the bomblet to penetrate roofs before bursting, projecting burning gel across interior surfaces. Each bomblet had an ignition envelope of approximately 2,000 square feet. Cluster carriers, E-46 and E-28 variants, dispensed the bomblets in calculated patterns to ensure uniform grid coverage across target zones. M47 napalm bombs served as pathfinders. Lead aircraft would drop these larger incendiaries to mark the target area for following bombers. The napalm created distinctive ground fires visible through overcast and smoke, providing aiming points for the main force. Airframe modifications began immediately. Ground crews removed most gun turrets from B-29 bombers, retaining only tail guns for rearward defense. The weight reduction totaled approximately 7,000 pounds per aircraft. This modification increased payload capacity, extended range, and reduced fuel burn at the planned attack altitude of 5,000 to 7,000 feet. The aircraft could now carry approximately 7 tons of incendiaries, more than double the bomb load of high-altitude missions. Ordnance sections on tinny and worked around the clock. Within 6 days, they assembled approximately 2,000 tons of incendiaries. Fusing tables were calibrated for low-altitude drops. Cluster spacing was calculated to ensure bomblet overlap across the target grid. Every calculation aimed at maximum coverage and ignition density. United States Army Air Forces Report 60B, dated February 1945, stated the objective plainly: maximum incendiary saturation to be tested on Tokyo urban industrial area. Weather permitting, the language was bureaucratic. The intent was total destruction. Adjusting altitude and munitions converted weather from adversary to ally. At 5,000 to 7,000 feet, jet stream effects were negligible. Bomb runs could be flown individually rather than in tight formation, allowing each aircraft to select optimal release points. Night dispersal reduced the effectiveness of Japanese flak and fighters. Anti-aircraft predictors were calibrated for high-altitude formations. Night fighters lacked the fuel reserves and radar coverage for sustained interceptions at low altitude. The logistics were brutal in their simplicity. More bombs, lower altitude, better accuracy, fewer losses. LeMay's staff calculated that one raid, executed with proper incendiary density and favorable wind, could remove approximately 1/4 of Tokyo's manufacturing base overnight. The projection was not optimistic speculation. It was based on Hamburg's documented firestorm dynamics, Tokyo's construction materials, and the proven performance of M69 bomblets. Weather forecasts for early March showed favorable conditions: clear skies, dry air, and sustained winds from the southwest. The winds were critical. They would spread fires and create the convective conditions necessary for a firestorm. Every element was aligning. The only question was whether the plan would survive contact with reality. Tokyo, Shitamachi, Honjo, Fukagawa, early March 1945. Low-level reconnaissance photographs lay spread across a light table in the intelligence section. Ward maps were annotated with block construction types, color-coded by materials. The annotations told a story of vulnerability. Japanese civil defense expected sporadic B-29 visits at high altitude. Air Defense Command maintained standing alerts. Firefighting brigades drilled regularly. Evacuation plans existed on paper. But nothing in Japanese planning anticipated saturation incendiary attack at low altitude with nearly 300 bombers converging on one city in a single night. Home Ministry data documented the problem with precision. Approximately 87% of structures in the target wards were timber construction with tarred paper roofs. Street widths averaged 10 to 15 feet. Building spacing was minimal. Entire neighborhoods formed contiguous fuel loads. The narrow lanes prevented effective fire breaks. Water mains were old and undersized. Firefighting equipment was insufficient for even localized fires, much less area conflagrations. Tokyo's air defense inventory appeared formidable in raw numbers but dissolved under scrutiny. Approximately 456 operational night fighters were distributed nationwide. Fewer than 2,000 heavy anti-aircraft guns, mostly Type 88 guns, were emplaced around major cities. Ammunition stockpiles were constrained by material shortages. Fuel allocations limited training hours for pilots and gun crews. Radar coverage was incomplete and operators were inexperienced compared to German or British standards. Warning systems functioned adequately for high-altitude daylight raids. The network could track formations approaching from the Marianas and provide several hours of advance notice. Civil defense protocols called for citizens to extinguish cooking fires, move to shelters, and prepare firefighting equipment. These measures worked against scattered incendiary drops. They would prove meaningless against deliberate firestorm conditions. Air Defense Command issued alerts on 8 March. Public evacuation was limited. Industrial workers remained at their posts. Firefighting resources were distributed according to pre-war plans that assumed conventional bombing patterns. Water pressure was adequate for normal demands but possessed no reserve capacity. Pumps and hoses dated from the 1920s and early 1930s. Cisterns provided backup water storage, but coverage was uneven across the target wards. Tokyo Metropolitan Police and Home Ministry ward summaries documented the city's construction in exhaustive detail. Intelligence analysts at 21st Bomber Command studied these documents, obtained through various sources before the war and during the conflict. The summaries provided building materials percentages, population density records, street layouts, and water infrastructure maps. Every data point confirmed Tokyo's exceptional vulnerability to incendiary attack. The urban geography amplified the risk. The Sumida River flowed through the eastern wards, creating wind corridors that channeled airflow during weather systems. Prevailing winds from the southwest would push flames northeast across the densest residential and workshop districts. The river itself would act as a barrier, trapping populations between advancing fire fronts and water. Material composition combined with wind corridors to create a contiguous ignition field. Civil defense capacity was fundamentally mismatched to incendiary saturation. The Japanese planning assumption that American bombers would continue high-altitude precision attacks was about to be shattered. Fire drills and bucket brigades could not counter 2,000 tons of purpose-designed incendiaries distributed across 16 square miles in under 3 hours. In less than 48 hours, aircraft from islands approximately 1,500 miles away would test the most combustible capital in the industrialized world. The preparations were complete. The weather was favorable. The target was mapped. The doctrine had been reversed. All that remained was execution. Marianas, Tinian, Guam, Saipan, 9 March 1945, afternoon through evening. The briefing theater boards displayed the mission details in block letters. Mission number 40, primary target, Tokyo urban area. Navigators copied wind forecasts onto their kneeboards. Armorers stacked cluster bombs on transport dollies outside the ordnance bunkers. 334 B-29s were tasked from the 73rd, 313th, and 314th bomb wings. Mission planners expected approximately 279 aircraft to reach and attack the target. The profile was unlike any previous mission. 5,000 to 7,000 feet altitude, night operations, independent bomb runs to maximize incendiary density over a grid footprint. Each crew was briefed to carry approximately 7 tons of ordnance. Planning tables referenced M69 clusters and M47 markers. Some documentation indicates figures like 166 clusters per aircraft for optimal target density, though unit records vary by wing and specific loading configurations. The objective was uniform coverage across the target grid, ensuring bomblet overlap and ignition certainty. Fuel logistics were staggering. More than 2 million gallons of aviation gasoline were drawn from an approximately 8,000-mile supply pipeline stretching from United States West Coast refineries through forward depots to the Marianas. Tank farms on each island maintained reserves sufficient for sustained operations. Fuel trucks moved in continuous cycles between storage and hardstands. 21st Bomber Command Bulletin No. 15, dated 9 March 1945, formalized the armament policy. Defensive armament restricted to tail guns. All others to be removed. The decision accepted higher exposure at low altitude in exchange for incendiary coverage and reduced fuel consumption. Planners predicted minimal night fighter interception given Japanese fuel constraints, pilot training deficiencies, and radar limitations. Crews gathered in briefing theaters across the 3 islands. Intelligence officers presented target maps, showing the dense grid of Shitamachi, Honjo, and Fukagawa wards. Weather officers confirmed favorable conditions. Clear skies over Japan, winds from the southwest at approximately 45 kilometers per hour at ground level, dry air, and minimal cloud cover. The wind forecast was critical. It would spread fires and create convective lift necessary for firestorm development. Navigators plotted routes that brought the bomber stream over Tokyo Bay from the southeast. Time on target stacking ensured continuous aircraft flow across the target area. Each bomber would make an independent run rather than flying in formation. This dispersed approach maximized coverage and prevented aircraft from interfering with each other's bomb runs. It also made the force harder to intercept, as Japanese fighters and anti-aircraft guns would face individual targets rather than concentrated formations. Flight engineers calculated fuel loads and consumption rates. The lower altitude profile reduced fuel burn compared to high-altitude missions but increased exposure time over enemy territory. Range calculations confirmed adequate reserves for the round trip of approximately 3,000 miles, accounting for winds aloft and combat maneuvering. Armorers loaded cluster bombs into B-29 bomb bays using hydraulic hoists. Each cluster weighed approximately 500 pounds and contained 38 M69 bomblets. The clusters were fused for altitude release, ensuring bomblet dispersion began above rooftop level. Loading proceeded through the afternoon and evening, continuing under floodlights as darkness fell. For the first time in the Pacific War, United States heavy bombers would penetrate an enemy capital virtually unarmed, trading defensive guns for fire. The tactical gamble was calculated and deliberate. Intelligence assessments predicted that Japanese night defenses lacked the coordination, fuel reserves, and training to mount effective resistance against low-altitude, dispersed attacks. Mission number 40 would test that prediction with nearly 300 aircraft and approximately 2,000 tons of incendiaries. Approaches over Tokyo Bay, 10 March 1945, 0003 through 0130 hours. Yokohama radar operators watched their scopes as the first returns appeared over the Pacific. The contacts were flying lower than expected. Altitude estimates put the formation between 5,000 and 7,000 feet, well below the normal B-29 cruise altitude. Pathfinder aircraft reached Tokyo first. They carried M47 napalm markers and had orders to bracket the eastern edge of Shitamachi Ward. At 0015, the first markers ignited on the ground, creating distinctive X patterns visible through scattered clouds. The napalm burned with intense orange light, providing clear aiming points for the main force. Weather conditions were nearly optimal. Winds measured approximately 45 kilometers per hour from the southwest. strong enough to spread fires rapidly but not so strong as to disperse smoke and reduce visibility for following bombers. Temperature and humidity were low. The air was dry. Every environmental factor favored combustion and fire propagation. The bombing sequence began at 00:15. Aircraft crossed the target at approximately 15-second intervals. Each bomber released its clusters independently, guided by radar returns, visual markers, and pre-briefed offset points. Within the first 20 minutes, approximately 100,000 M69 bomblets seeded a grid covering approximately 4 square miles. Japanese anti-aircraft defenses responded immediately. Searchlights swept the sky. Type 88 anti-aircraft guns opened fire. Tracer rounds arced upward. But the guns were calibrated for high-altitude formations. Predictors struggled to track individual aircraft at 5,000 to 7,000 feet. Fire control solutions degraded in the confusion of multiple targets at varying altitudes and headings. Approximately 15 night fighters scrambled from Atsugi and Chofu airfields. Nakajima J-1N Irving and Kawasaki Ki-45 Toryu interceptors climbed toward the bomber stream. Pilots reported difficulty acquiring targets against the ground clutter of urban lights and growing fires. Radar intercept officers struggled to separate individual contacts. No confirmed kills were recorded during the first hour of the attack. Air crews began reporting unusual conditions within 30 minutes of the first bomb releases. Cockpit temperatures rose noticeably. Outside air temperature gauges climbed above normal readings. Observers in the tailgun positions reported heat distortion in the air below. The fires were already coalescing. Intervalometer settings had been adjusted for linear coverage patterns. Bombardiers used both radar and visual cues for release points. The planned altitude band of 5,000 to 7,000 feet was maintained across most of the force. Bombing accuracy exceeded expectations from previous high-altitude missions. The combination of lower altitude, individual bomb runs, and reduced wind effect produced tight clustering of bomblets within the target grid. By 0100 hours, fires had merged into continuous fronts. Aerial observers reported visibility deteriorating rapidly. Smoke columns rose to 10,000 feet and higher. The characteristic rotation of a firestorm began to appear, fire fronts connecting in circular patterns around a central updraft zone. Ground temperatures were climbing toward levels that would spontaneously ignite combustible materials without direct flame contact. United States Strategic Bombing Survey Field Report Number 52 documented conditions at this phase. By 0100 hours, fires coalesced into continuous fronts. Visibility nil. Air temperature within aircraft rose to 140 degrees Fahrenheit. Crews in later waves reported flying through thermal turbulence strong enough to require control inputs. The heat rising from Tokyo was creating its own weather. Japanese anti-aircraft fire became sporadic and disorganized. Searchlight batteries lost power as electrical distribution failed in burning wards. Gun crews abandoned positions as fires approached. The air defense system was collapsing under the weight of the attack and the spreading fires. At 0130, thermodynamic thresholds were crossed. The first true firestorm in Tokyo's history was fully developed. The attack would continue for another 90 minutes, adding fuel to a conflagration already beyond any possibility of control. Shitamachi, Honjo axis, 0130 through 0300 hours, 10 March 1945. Aerial reconnaissance film from later waves showed rotating convection columns rising from the city center. Ground reports transmitted by wire before communications failed logged collapsing water pressure throughout the target area. Tokyo was entering a thermodynamic state that had been seen before only in Hamburg and Dresden. Fire fronts joined along both banks of the Sumida River. Individual building fires merged into block fires. Block fires merged into district fires. District fires created a single, continuous combustion zone covering approximately 16 square miles. Updrafts towered to 15,000 feet, visible to bomber crews miles away. Measured and estimated ground temperatures approached 1,000 degrees Celsius in the core zones. Civil defense reports transmitted before telephone lines burned documented conditions that exceeded all planning scenarios. Oxygen depletion became widespread as the firestorm consumed available air. People in shelters suffocated as flames overhead drew oxygen from below-ground spaces. Clothing ignited spontaneously on individuals hundreds of feet from direct flames. Shingled roofs burst into fire without ember contact. The heat itself had become a weapon. Firefighting efforts collapsed within the first hour. Hydrants ran dry as water mains ruptured from heat stress and physical damage. Pumps could not maintain pressure against the demand of thousands of simultaneous ignition points. Reserve cisterns were exhausted within minutes. Fire brigades retreated, then disbanded as their positions became untenable. The firestorm was beyond human intervention. Destruction metrics accumulated through the night and following days. Approximately 267,000 buildings were consumed. Tokyo Metropolitan Police compiled casualty rolls during the immediate aftermath, initially logging approximately 105,400 deaths. Later reconciliation adjusted the figure toward approximately 88,000 confirmed dead, with the range reflecting wartime record attrition and the difficulty of accounting for complete families lost without survivors to report them. The technical linkage between weapon design and outcome was direct. Each M69 bomblet had an ignition envelope of approximately 2,000 square feet. This specification aligned precisely with Tokyo's block density and building spacing. Bomblet clustering from E-series carriers ensured overlap, generating continuous flame fronts rather than isolated fires. The result was predictable from the weapon specifications and the target geography. Tokyo Metropolitan Police wartime ledgers documented the progression with bureaucratic precision even as the disaster unfolded. Ward-level losses were recorded. Utility failures were logged. Casualty estimates were revised upward hour by hour. The records provide a real-time account of urban collapse documented by officials working in structures that would themselves burn before dawn. Japanese firefighting doctrine was based on containing spot fires through organized bucket brigades and pump stations. The approach worked for earthquake fires and conventional bombing. It proved completely insufficient against area saturation incendiary bombing. Pump capacity and reserve cisterns were outpaced within the first 15 minutes of sustained bombardment. Conventional firefighting methods required isolation of individual fires, an impossibility when thousands of fires ignited simultaneously across miles of contiguous urban fabric. The urban fuel load was the fundamental vulnerability. Timber construction with paper interior walls and tarred paper roofing created structures that were essentially prepositioned kindling. Wind channelization along the Sumida River ensured uniform fire spread. Narrow streets prevented effective fire breaks. High population density meant that evacuation routes were immediately overwhelmed. Every element of Tokyo's urban design amplified the incendiary effect. Survey teams working in daylight hours after the raid measured ground temperatures still above 200 degrees Celsius in some areas. Steel beams had softened and sagged. Stone foundations had cracked from thermal shock. Brick chimneys stood alone amid acres of ash. The physical evidence confirmed that peak temperatures during the firestorm had reached levels normally associated with industrial furnaces. Within 120 minutes of the first Pathfinder markers, surveys indicated approximately 50% of Tokyo's light industrial capacity in the targeted wards had ceased functioning. The workshops that produced subassemblies, tools, fixtures, and gauges were gone. The workers were dead, displaced, or injured. The materials were destroyed. The industrial infrastructure supporting Japan's war production had suffered catastrophic disruption in a single night. Over Tokyo and surrounding airfields, approximately 0200 through 0400 hours, 10 March 1945. Night fighter scramble boards at Atsugi and Chofu airfields showed continuous launch sequences. Interceptors took off in darkness, climbed toward the bomber stream, and found themselves operating in conditions their training had not anticipated. Searchlights failed in the smoke. Radio traffic broke down as ground stations lost power. The defensive system was disintegrating. Nakajima J-1N, Irving twin-engine night fighters carried airborne intercept radar but lacked the power and training to exploit it effectively against dispersed, low-altitude targets. The The radar sets were early-generation equipment with limited range and poor discrimination against ground clutter. Operators struggled to separate individual bomber contacts from the thermal disturbance rising from Tokyo. Visual acquisition was nearly impossible with smoke columns reaching 15,000 feet and obscuring everything below. Kawasaki Ki-45 Toryu fighters were faster but lacked radar entirely. Pilots relied on ground-controlled intercept directions and visual acquisition. Both methods failed against the American attack profile. Ground controllers lost situational awareness as communications degraded. Smoke and fire glow obscured visual references. Interceptor pilots found themselves flying through smoke, turbulence, and disorienting light conditions with no clear targets. Japanese Army Air Force combat report from 10 March documented the frustration. Enemy altitude unexpectedly low. Defensive fire ineffective. Fire pattern indicates precise coordination. The report noted that American bombers were operating individually rather than in formation, making concentrated interception impossible. Each aircraft had to be tracked and engaged separately. With approximately 279 bombers crossing the target over a 3-hour period, the handful of available interceptors was hopelessly outnumbered. United States losses totaled approximately 14 B-29s to all causes: anti-aircraft fire, mechanical failure, and operational accidents. The loss rate of approximately 5% was below some European theater of operations night bombing missions despite the lower altitude and proximity to defenses. The gamble of stripping defensive armament and flying at medium altitude had paid off. Anti-aircraft artillery was the primary Japanese defense, but it proved inadequate. Type 88 guns were capable weapons when properly employed, but they were designed for high-altitude formation bombing. Predictors calculated firing solutions based on expected target altitude, speed, and heading. The American bombers flew lower and faster than the guns were calibrated for. Individual bomb runs from varying directions prevented concentrated barrage fire. Ammunition expenditure was high but effectiveness was minimal. Tailgun retention proved sufficient for self-defense. American gunners reported few aggressive intercept attempts. Most Japanese fighters that closed to firing range broke off after encountering return fire. The psychological effect of defensive fire was significant even when hit probability was low. Japanese pilots, already constrained by fuel and training limitations, showed reluctance to press attacks against bombers that could still defend themselves. Energy management at low altitude gave American crews a significant advantage. B-29 bombers at 5,000 to 7,000 feet could dive to gain speed or climb to evade without entering jet stream turbulence. Japanese interceptors operating near their service ceiling had less maneuvering margin. The altitude band chosen for the attack optimized both bombing accuracy and defensive survivability. Night ingress denied Japanese defenders the critical window to mass forces. In daylight operations, radar could track incoming formations from hundreds of miles away, providing time to scramble interceptors, position anti-aircraft batteries, and coordinate defenses. Night operations compressed the timeline and degraded the effectiveness of visual observers. By the time Japanese defenders realized the scale and nature of the attack, bomber crews were already over the target. Command circuits degraded throughout the attack. Telephone lines burned. Radio stations lost commercial power and switched to emergency generators, then lost those as well. Courier systems broke down as roads filled with refugees. Air Defense Headquarters lost contact with subordinate units. The organizational structure collapsed as the physical infrastructure supporting it was destroyed. Searchlights went dark as electrical distribution failed. Anti-aircraft ammunition supplies dwindled without resupply. Gun crews evacuated positions threatened by advancing flames. And the bomb line continued unimpeded. Tokyo's air picture went blind at the moment when accurate information was most critical. The defenders fought individually without coordination against an attack that was centrally planned and precisely executed. Marianas and supply echelons. March through April 1945. Petrol oil lubricants farm gauges showed steady drawdown and replenishment cycles. Ordnance teams refilled cluster bomb trays in hardstand areas. Maintenance rosters pinned to hangar doors tracked aircraft status and readiness rates. The operation over Tokyo was not an isolated maximum effort. It was the beginning of a sustained campaign enabled by logistics. Throughput calculations confirmed the scale of the operation. Each sortie consumed approximately 7,000 gallons of aviation fuel. Each aircraft dropped approximately 13,000 pounds of incendiary bombs. Multiplied across nearly 300 aircraft, mission number 40 consumed approximately 2 million gallons of fuel and delivered approximately 1,800 tons of ordnance, all in a single night. Manpower sustained the tempo. On Tinian alone, approximately 1,500 mechanics maintained the B-29 fleet. Approximately 900 armorers assembled, fused, and loaded bombs. Approximately 600 refueling personnel operated tank trucks and pumps. Around-the-clock shift rotations enabled mission turnarounds at intervals of 24 to 72 hours. The human infrastructure supporting the bombing campaign was as important as the aircraft themselves. Comparative production figures illustrated the disparity between American and Japanese logistics. The Pacific Supply Pipeline delivered approximately 200,000 tons per month of bombs, fuel, and related ordnance to forward bases. Japanese domestic aviation fuel production totaled less than 80,000 barrels per month, constraining pilot training and operational sorties. Japan could not match American throughput in any category of war material. 20th Air Force Supply Report from March 1945 stated with characteristic bureaucratic understatement, current operational tempo sustainable. Enemy defensive aviation constrained by fuel and serviceability. The assessment was accurate. American planners could schedule raids at will, limited only by weather and target selection. Japanese defenders operated under constant fuel and ammunition rationing. CB's naval construction battalions had built the infrastructure that made sustained operations possible. Runways on Tinian, Guam, and Saipan were engineered to support fully loaded B-29 takeoffs and landings. Hardstands provided parking and maintenance space for hundreds of bombers. Taxiways connected the operational areas. Fuel storage farms held millions of gallons in above-ground tanks. Ordnance bunkers protected bomb stocks from accidental detonation. The construction effort represented months of work by thousands of personnel, completed while combat operations against bypassed Japanese garrisons continued on neighboring islands. Tankers delivered fuel from West Coast refineries to forward depots at approximately 2-week intervals. Cargo vessels brought bombs, spare parts, maintenance equipment, and consumables on similar schedules. The maritime supply line operated continuously, replacing expended ordnance and fuel faster than missions could consume them. Stockpiles grew rather than diminished even as operational tempo increased. Industrial depth translated into operational persistence. Each incendiary raid over Japan replicated the March 10 pattern. Low altitude, night operations, maximum bomb load, minimal defensive armament. The tactics were proven. The weapons were effective. The logistics were sustainable. Mission number 40 became the template for systematic urban destruction. Identical raids on Nagoya, Osaka, and Kobe were scheduled within days of the Tokyo attack. Nagoya burned on 11 March. Osaka burned on 13 March. Kobe burned on 16 March. The pattern repeated with industrial precision. Intelligence selected targets. Weather forecasters identified favorable conditions. Ordnance crews loaded bombs. Crews flew missions. Reconnaissance aircraft photographed results. Planners selected the next target. Maintenance crews kept aircraft flying despite the demanding operational tempo. Engine changes were completed overnight. Battle damage was repaired between missions. Supply clerks tracked parts inventories and submitted requisitions months in advance to ensure availability. The logistics infrastructure was both vast and efficient, embodying industrial methods applied to warfare. Japanese defenders could observe the pattern but lacked the resources to counter it effectively. Anti-aircraft ammunition was rationed. Fighter fuel allocations declined. Pilot training hours decreased. Radar coverage remained incomplete. Every defensive metric trended downward as American offensive capabilities remained constant or improved. The disparity was mathematical and irreversible. With stockpiles secure and loss rates acceptable, 21st Bomber Command expanded target lists and increased sortie rates. 66 additional urban raids would be conducted before August 1945. The campaign that began over Tokyo on 10 March became a systematic effort to destroy Japan's urban industrial base through fire. The method was proven. The resources were available. The will was present. Industrial democracy at war demonstrated its capacity for sustained, overwhelming force. Tokyo, Dawn Reconnaissance, 10 March 1945. Photographic interpreters aligned overlapping reconnaissance frames on light tables at Guam and Tinian. Grease pencils outlined voids where wards had stood 12 hours earlier. The mosaics measured approximately 15.8 to 16.0 square miles burned, an area larger than Manhattan south of Central Park. United States Strategic Bombing Survey later estimated that approximately 50% of Tokyo's industrial capacity in the affected areas was eliminated in one night. The calculation included workshops, small factories, warehousing, transportation infrastructure, and worker housing. The loss was not just buildings, it was the entire production ecosystem that supported Japan's war effort. Administrative impact extended beyond physical destruction. Fukagawa Ward was largely gone. Hanjo Ward existed mostly as ash. Asakusa was burned out. Municipal utilities, water, electricity, telephone, were crippled throughout eastern Tokyo. Transportation hubs were destroyed or impassable. Rail lines were blocked by debris. Roads were clogged with refugees. The city's ability to function as an administrative and industrial center was severely compromised. Emergency cabinet session notes from the evening of 10 March acknowledged grave paralysis of production. The language was restrained, but the implications were clear. Japan's capital and largest industrial center had suffered catastrophic damage in a single night. The attack model that produced this result could be, and would be, repeated against other cities. Displacement exceeded 1 million people from the burn zones. Refugees crowded into western Tokyo, overwhelming available shelter and social services. Families lost homes, possessions, and often members. The social cohesion necessary for industrial production and civil order was disrupted on a massive scale. Workers who survived had no homes to return to. Workshops that survived had no workers to operate them. Japanese leadership had expected attritional bombing spread over months or years, similar to the European experience. The Allies had bombed German cities progressively, allowing time for adaptation, dispersal, and reconstruction between attacks. The Tokyo raid delivered a shock loss in a time frame that prevented adaptation. One night eliminated what months of high-altitude precision bombing had failed to degrade. Loss of small shop networks broke the supply of fixtures, gauges, and subassemblies to larger manufacturing plants. The decentralized production system that had frustrated American precision bombing now became a catastrophic vulnerability. When the workshops burned, the entire supply chain collapsed. Even factories that survived intact could not operate without the parts, tools, and components produced in the destroyed wards. In comparative terms, one night over Tokyo exceeded cumulative destruction achieved in a week of sustained operations against Germany's Ruhr industrial region. The Ruhr campaign had required hundreds of sorties over multiple days against dispersed targets. Tokyo absorbed equivalent destruction in under 3 hours. The difference was target selection and weapon optimization. Incendiaries against wood construction proved devastatingly efficient. Reconnaissance photographs documented the scope with clinical precision. Pre-raid mosaics showed dense urban fabric, streets, buildings, and infrastructure clearly visible. Post-raid mosaics showed blank areas, no buildings, no streets, no infrastructure. Entire neighborhoods had been reduced to ash and rubble. Photo interpreters measured the burn zones with planimeters, calculating area and comparing to pre-raid maps. The human cost was documented through multiple channels. Police casualty rolls, hospital admission records, missing person reports, and burial registrations all contributed to the final accounting. Initial estimates exceeded 100,000 dead. Later reconciliations settled near 88,000 confirmed fatalities. Acknowledging that complete accounting was impossible, when entire families perished without survivors to report losses. Industrial surveys conducted in subsequent weeks confirmed the production impact. Machine shops stood empty. Tool and die workshops no longer existed. Small manufacturers of gauges, jigs, and fixtures were gone. The network of subcontractors supplying parts to major assembly plants was severed. Aircraft production declined not because assembly plants were hit, but because the supply of components dried up. The psychological impact on Japanese leadership was profound though difficult to document precisely. The raid demonstrated that American forces possessed both the capability and willingness to systematically destroy Japanese cities. The conventional wisdom that Japan's geography and distance provided protection was shattered. If Tokyo could be burned in one night, any city in Japan was vulnerable. Strategic implications extended beyond Tokyo. The raid validated a method that could be replicated across the Japanese urban system. Every major city shared Tokyo's vulnerabilities: wood construction, high density, inadequate fire protection, and constrained civil defense. The template was proven. The resources were available. The precedent was established. 10 March 1945 became an inflection point in the Pacific War. Before that date, strategic bombing of Japan was ineffective and uncertain. After that date, urban destruction became systematic and predictable. The night Tokyo burned marked the transition from experimental tactics to industrial-scale implementation of incendiary warfare. Guam, 11 through 20 March 1945. Signal center typewriters clattered as communications staff prepared after-action reports. A cable addressed to General H. H. Arnold at Army Air Forces headquarters summarized the Tokyo results and recommended immediate follow-on operations. Post-raid messages attributed to LeMay's communications stated, "Results far exceed expectation. Recommend immediate repetition." The recommendation was implemented with characteristic speed. Nagoya was attacked on 11 March, one day after Tokyo. Osaka burned on 13 March. Kobe was struck on 16 March. The tactics and munitions replicated the Tokyo model. Low altitude, night operations, incendiary saturation, minimal defensive armament. Cumulative destruction across these four cities totaled approximately 56 square miles within 10 days. Command analysis cited per sortie effectiveness approximately 6 times greater than previous high-altitude precision raids. The calculation included bomb tonnage delivered, target area destroyed, and losses sustained. Every metric favored low-altitude incendiary attack over high-altitude precision bombing. The doctrinal reversal that LeMay implemented in February was validated by March results. United States Army Air Forces Communique No. 166 stated formally, "Operation Meeting House conclusively validates low-altitude incendiary saturation." The communique used the official code name for the Tokyo raid and made explicit what operational staff already knew. The method worked. Debate within military circles focused not on whether to continue but on target selection and scheduling. Moral and ethical debates occurred at higher command levels and in political circles, but operational staff focused on replicability and logistics feasibility. The questions asked were tactical and logistical. Which cities should be targeted next? What was the optimal interval between raids? How should weather forecasting and bomb load be adjusted for different urban densities? Could the tempo be sustained through summer and into autumn? Demonstrated density thresholds combined with predictable wind regimes and sustained supply lines produced a repeatable campaign plan for urban targets. Intelligence officers compiled lists of Japanese cities ranked by industrial importance, population, and vulnerability to incendiary attack. Meteorologists provided seasonal wind forecasts. Ordnance planners calculated bomb requirements. The systematic destruction of Japan's urban infrastructure became an engineering problem with known solutions. Mission planning evolved into routine. Target folders included pre-raid reconnaissance mosaics, ward maps showing construction types, population density estimates, industrial facility locations, and expected wind conditions. Bombing altitudes and incendiary loads were standardized. Pathfinder techniques were refined. The learning curve from Tokyo and subsequent raids produced incremental improvements in execution. Loss rates remained acceptable. Japanese night defenses proved unable to adapt to the low-altitude incendiary tactics. Anti-aircraft effectiveness declined as ammunition stocks dwindled and experienced gun crews were killed or reassigned. Night fighter interceptions remained sporadic and ineffective. American crews faced danger from mechanical failure and weather more than enemy action. The industrial logic was ruthless and clear. Each city destroyed reduced Japan's war production capacity. Each raid displaced workers and disrupted transportation. Each firestorm consumed materials that could not be replaced. The cumulative effect was economic strangulation achieved through urban destruction. Japan's ability to sustain military operations depended on industrial output. Industrial output depended on urban infrastructure. Urban infrastructure was highly vulnerable to incendiary attack. With the method validated, 66 additional urban raids would be conducted before August 1945. The campaign expanded to include medium-sized cities with populations between 50,000 and 200,000. By summer, the target list included cities that would have been considered too small for strategic bombing in Europe. Every urban center with war production became a potential target. The progression from Tokyo to systematic urban bombing occurred in weeks, not months. Operational tempo accelerated as logistics caught up with tactical innovation. Bomb stockpiles on the Marianas grew faster than missions could expend them. Fuel reserves remained adequate. Aircraft availability improved as maintenance procedures were refined. The campaign achieved industrial efficiency in the destruction of industrial capacity. LeMay's telegram and the rapid follow-on raids established a pattern that would continue until Japan's surrender. The innovation was not technological, incendiary bombs were well-understood weapons. The innovation was operational, matching weapon characteristics to target vulnerabilities and executing at scale with industrial persistence. Tokyo demonstrated the concept. The campaign that followed demonstrated the execution. Tokyo, Washington Analytical Channels, April through August 1945. Comparative analysis tables circulated through military planning staffs, contrasting incendiary campaign results against projections for atomic weapons still under development. The numbers revealed unexpected equivalencies that would shape post-war assessments of strategic air power. By mid-1945, approximately 67 Japanese cities had been attacked by incendiary area bombing. Approximately 40% of urban space nationwide was uninhabitable, destroyed, severely damaged, or evacuated. Cumulative air raid civilian deaths approached 330,000 prior to the atomic strikes on Hiroshima and Nagasaki. The scale of destruction achieved with conventional weapons was extraordinary. Campaign totals documented the systematic nature of the urban offensive. Major cities were struck multiple times. Medium cities were hit once but thoroughly. Small cities with specific industrial facilities were targeted selectively. The cumulative bomb tonnage exceeded 100,000 tons of incendiaries. Millions of structures were destroyed. Millions of people were displaced. Japan's urban industrial base was progressively dismantled through fire. Comparative fatality assessments provided sobering context. Tokyo on 10 March killed approximately 88,000 people with conventional incendiary munitions. Hiroshima on 6 August and Nagasaki on 9 August produced initial fatality estimates in similar ranges. Hiroshima approximately 70 to 80,000 immediate deaths. Nagasaki approximately 40,000 immediate deaths. Tokyo's single-night conventional raid met or exceeded the immediate lethality of individual atomic attacks. United States Strategic Bombing Survey urban bombing studies and post-war evaluations contrasted conventional versus atomic destructive efficiency. The atomic weapons delivered their effects instantaneously and from a single aircraft. Conventional incendiary raids required hundreds of aircraft and hours of execution. But the end result, urban areas rendered uninhabitable and populations killed or displaced, was comparable in scale. The distinction mattered for strategic planning but less for the populations experiencing the attacks. A family burned in Tokyo on 10 March was as dead as a family vaporized in Hiroshima on 6 August. A city rendered non-functional by firestorm was as militarily useless as a city destroyed by atomic blast. The means differed, the strategic outcome was similar. Atomic weapons would come to symbolize strategic air power and the destructive potential of modern warfare. The images of mushroom clouds and the physics of nuclear fission captured public imagination. Hiroshima and Nagasaki became synonymous with ultimate warfare. But incendiary tonnage combined with favorable wind and combustible urban materials had already demonstrated mass lethality before any atomic device was employed operationally. The March template guided late-war city targeting and undermined Japanese industrial and administrative resilience before capitulation. Each raid reduced production capacity, consumed irreplaceable materials, and displaced skilled workers. The cumulative effect was industrial collapse achieved through persistent application of conventional munitions optimized for the target environment. Strategic assessments debated whether atomic weapons were necessary to compel Japanese surrender or whether conventional bombing combined with naval blockade would have achieved the same result. The debate continues in historical literature. What remains undisputed is that conventional incendiary bombing had already brought Japan to the brink of economic collapse by August 1945. Production statistics told the story. Steel output declined 83% from peak production. Aircraft manufacturing fell 75%. Merchant shipping losses exceeded 50% of pre-war tonnage. Rail transportation was severely degraded. Food distribution networks were disrupted. Every indicator of industrial capacity and economic health trended toward collapse. The atomic strikes on Hiroshima and Nagasaki provided a psychological shock and a political justification for surrender that allowed Japanese leadership to accept defeat without admitting conventional military failure. The emperor's surrender broadcast cited a new and most cruel bomb as justification for ending the war. The narrative focused on atomic weapons rather than the cumulative destruction of months of conventional bombing. Long before a nuclear device was used in combat, air power alone had demonstrated the capacity to render a major capital non-functional in hours. Tokyo on 10 March proved that conventional munitions, properly employed against vulnerable targets, could achieve strategic effects previously considered impossible without years of siege or months of sustained bombardment. The firestorm was as decisive as the atom. It simply lacked the dramatic symbolism and scientific mystique. The incendiary campaign established doctrinal precedents that would influence air power theory for decades. The effectiveness of area bombing against urban industrial targets was documented and quantified. The importance of matching weapons to target vulnerabilities was proven. The necessity of logistics and sustained operational tempo was demonstrated. These lessons informed strategic bombing doctrine throughout the Cold War and beyond. 10 March 1945 demonstrated that approximately 2,000 tons of conventional incendiaries, properly delivered against combustible urban construction, could neutralize a capital in hours. The result was measurable in tonnage, temperature, and square miles. No rhetoric required. The numbers spoke for themselves. Japan, May through August 1945. United States Strategic Bombing Survey interview schedules filled notebooks as analysts questioned Japanese industrial managers, government officials, and military officers. Factory yard gauges stood frozen, recording the last measurements taken before facilities shut down. The cumulative impact of urban bombing was measured in production statistics that documented industrial collapse. Steel output declined approximately 83% from peak wartime production. Aircraft manufacturing fell approximately 75%. Machine tool production dropped to negligible levels. Merchant shipping losses exceeded 50% of pre-war tonnage, disrupting raw material imports and internal distribution. Every industrial metric showed severe degradation accelerating through spring and summer 1945. Rail and barge distribution networks were degraded by city destruction and fuel scarcity. Rolling stock was damaged or destroyed in urban raids. Trackage was disrupted. Barge traffic on inland waterways declined as ports and terminals burned. The transportation system that moved materials between production facilities, from factories to military depots, and from agricultural regions to cities was progressively paralyzed. Post-March evacuations displaced more than 1 million people from Tokyo alone. Similar displacements occurred in every major city attacked. The evacuations drained labor pools and reduced workshop utilization. Skilled workers left urban areas. Families relocated to rural regions. The concentration of labor necessary for industrial production was dispersed across the countryside, making coordination and supervision impossible. United States Strategic Bombing Survey final report, published July 1946, concluded, urban destruction through incendiary bombardment rendered continuation of war materially impossible. The assessment was based on comprehensive analysis of Japanese production records, interviews with officials, and inspection of industrial facilities. The survey documented how housing loss and transport disruption severed the supply of parts, tools, and skilled labor necessary for war production. Imperial plans for protracted defense presumed stable urban production could sustain military operations through 1946 and into 1947. Strategic planning assumed that dispersal of facilities and mobilization of remaining resources could compensate for material losses. In practice, urban destruction made these plans impossible to execute. The production base necessary for sustained resistance no longer existed. Workshop losses were particularly devastating to Japanese military production. Large assembly plants could be rebuilt or relocated, but the networks of small suppliers producing specialized components could not be reconstituted quickly. The destruction of tool-and-die shops eliminated the capacity to produce the precision equipment necessary for manufacturing aircraft engines, optical sights, and fire control mechanisms. Without these components, assembly of finished weapons ceased even where assembly facilities survived intact. The March 10 raid became a keystone event in the industrial collapse timeline. The method was proven that night. Repetition across the archipelago followed systematically. The cumulative effect was industrial paralysis achieved through persistent destruction of urban infrastructure. Each raid compounded the effects of previous raids, creating cascading failures throughout the production system. Even without considering naval blockade effects, which severely constrained raw material imports, urban fire alone had cornered Japan's war economy. The American submarine campaign strangled external supply lines. The incendiary bombing campaign destroyed internal production capacity. Together, these two forms of economic warfare made continued military resistance materially impossible regardless of leadership will or troop morale. Japanese industrial production in August 1945 represented a fraction of January 1945 capacity. The decline was steeper than could be explained by material shortages or labor conscription alone. Urban destruction eliminated the physical infrastructure and social organization necessary for industrial activity. Factories without workers, workshops without tools, and transportation systems without terminals could not produce war materials no matter what resources remained theoretically available. The industrial collapse documented by post-war surveys confirmed that strategic bombing achieved its fundamental objective, rendering the enemy incapable of continuing organized military resistance. The means, incendiary destruction of urban areas, was controversial. The outcome, industrial paralysis, was undeniable. Japan surrendered not because its armies were defeated in the field but because its capacity to sustain those armies was eliminated. Post-war Tokyo, 1946 through 1950. Reconstruction maps spread across city planners' desks in temporary government offices. Zoning overlays replaced destroyed wards with redesigned street grids and updated building codes. The physical scars of 10 March 1945 would heal within years, but the historical implications would resonate for decades. Tokyo metropolitan government records documented rapid reconstruction. Approximately 95% of the devastated zone was rebuilt within 5 years. The reconstruction incorporated fire-resistant construction standards, wider streets, and improved urban planning. The new Tokyo emerged from the ashes with infrastructure superior to what existed before the war, though the cost in lives and cultural heritage was incalculable. Urban fabric shifted toward concrete, steel, and tile construction. Building codes mandated fire-resistant materials and structural standards designed to prevent firestorm propagation. Street widths were increased to serve as fire breaks. Water distribution systems were upgraded with redundancy and capacity margins. The lessons of 10 March were encoded into the physical structure of post-war Tokyo. Memory and historical assessment of Operation Meeting House continued to evolve. General Curtis LeMay later reflected on the incendiary campaign with characteristic bluntness. "If we'd lost the war, we'd have been tried as war criminals." The statement acknowledged the moral ambiguity of strategic bombing directed against civilian populations, even when justified by military necessity and conducted within the legal framework of the time. Historiography continues to debate the necessity and morality of the incendiary campaign. Critics argue that urban area bombing constituted indiscriminate warfare against civilians disproportionate to military objectives. Defenders argue that Japan's decentralized production system made urban areas legitimate military targets, and that the bombing shortened the war, ultimately saving lives by avoiding a ground invasion. The debate involves moral philosophy, military ethics, and historical interpretation that remains unresolved. The operational facts remain uncontested regardless of moral judgment. Incendiary saturation achieved its military objective by exploiting target vulnerabilities, combustible construction materials, favorable wind patterns, and high urban density. Approximately 2,000 tons of M69 bomblets properly delivered over combustible urban construction created firestorm conditions that neutralized Tokyo's industrial capacity in under 3 hours. The outcome was predictable from weapons specifications and target analysis. Operation Meeting House served as a doctrinal inflection point for strategic bombing theory worldwide. Military planners studied the raid as a case study in matching weapons to targets and executing at operational scale. The success of low-altitude incendiary tactics against urban areas influenced procurement decisions. Stockpiles of incendiary munitions were maintained by major military powers throughout the Cold War. Civil defense planning incorporated lessons from Tokyo and other firestorm cities. Fire-resistant construction became standard in urban planning. Emergency response systems were designed with mass casualty scenarios in mind. Water distribution networks included redundancy and reserve capacity. The vulnerability demonstrated by Tokyo informed defensive preparations globally. The incendiary campaign also influenced arms control and international humanitarian law. The Geneva Conventions were updated after World War II to provide greater protection for civilian populations during wartime. Debate over strategic bombing contributed to evolving legal standards regarding proportionality, discrimination between combatants and non-combatants, and acceptable military targets. The legacy of cities like Tokyo, Hamburg, and Dresden shaped international norms regarding aerial warfare. Post-war strategic bombing surveys conducted by United States and Allied personnel documented the campaign's effects with scholarly rigor. The surveys provided detailed analyses of bomb damage, industrial disruption, economic impact, and civilian casualties. These documents became primary historical sources, offering comprehensive data about the most intensive bombing campaign in history. The surveys informed post-war military doctrine and provided empirical foundations for strategic air power theory. Memorials and remembrance ceremonies in Tokyo preserve the memory of 10 March 1945. The Tokyo Air Raid Memorial Hall documents the civilian experience through artifacts, photographs, and survivor testimony. Annual commemorations honor the dead and educate younger generations about the war's impact on civilian populations. The historical memory remains active in Japanese culture and education. 10 March 1945 demonstrated that approximately 2,000 tons of conventional incendiaries, properly delivered against optimal target conditions, could neutralize a major capital in hours. The result was measured in tonnage, temperature, and square miles, not rhetoric. The number 88,000 dead represents the human cost. 16 square miles of destruction represents the physical impact. 50% industrial capacity lost represents the strategic effect. These figures document a night when fire became the decisive weapon in modern warfare. A night when military planning, industrial production, and urban geography converged in catastrophic consequences that remain relevant to military history and strategic thought.